Welcome back, guys, to the daily session of lead code questions. We'll be going through three questions, one each from easy, medium, and hard bucket, and we'll discuss approaches and solutions for them. Okay.
Puni, do you want to start recording?
I have already started recording.
Oh, sorry. Go ahead.
Okay. Yeah. So let me get started, and with the we'll start with the first easy problem from the bucket. So this is a problem, and what they have mentioned is you're given a list of words. This is your input, and what you have to output is the words in this array.
Hey, you have not shared your screen.
Oh, I'm sorry. Are you able to see now?
Yeah.
Okay, sorry for that. So what we are given is a list of words, which is the input, and what we have to output is the words which can be spelled out or which can be typed in a single row of the keyboard. So suppose the element, the word hello. So for typing hello, we'll have to use H from the second row, T from the first row. So this should not be in our output. Whereas the other one, like Alaska, the entire word can be spelled out using characters in the second row, A, L, A, S, K, and A. So this should be in our output, similar to dad and then peace. So out of which you can see only Alaska and dad are the two words which can be spelled out. All of the characters in the word are in the same row of the keyboard. So that's what we have to do. Just find out which words can be typed using the characters in the same row, and that should come in our output, right? And from the node point, they have said even if you have multiple characters, you can assume them, they can be used. It's not necessary that you can use those characters only once. You can use them multiple times. Okay. So any approaches, ideas?
I solved this problem using hash maps. So I just created like for each character which row they belong to. Okay. So let's say QWERT. If for these entries in the hash map, I'd store 1. For ASDF, it's a constant space because I'm only storing all the alphabets. So that's a constant space requirement. And for each character, I'm checking like if like the first time if the hash map value changes, like if it's going 1 1 1 and then it moves to another, then I break it and I don't consider it as a valid word. But if all the characters are in the same hash like value of the app is same, then it's a valid word that we can type in the same row. The time complexity would be like the maximum of characters into n words. So whatever the length of the maximum string is into the number of words.
Right. So you're essentially taking the constant space complexity because the number of characters in the keyboard are very limited. It's always going to be same.
Yeah.
Right. So one question: do you need a hash map, or you can do it with some other data set like a hash set?
Yeah, hash set like.
Right. So why do we need a hash set? And so essentially the question is when do we need a hash map and when do we need a hash set?
Those are, I guess, ordered in some way. Like in hash set, the elements stored are ordered in some way. So I think searching would be faster, I guess.
No, both hash set and hash map will have the same internal saving structure. It's just that hash map is usually used when you have some additional information to be stored corresponding to that key, right? Here, if you create 3 different arrays or 3 different sets, you can directly find out the first one, second, and third one, right? You don't need essentially anything additional like There's no frequency of characters or there's no position of characters that you want to attribute to each of the character. Like Q is first, W is second. So what you need essentially is just the characters which are in the set one.
Okay. Yeah, got it.
But how you know when you cross two different sets? Then you have to somehow keep track of, what set you are currently in.
Right. So what you can do is just take first character, okay, and find out of three which set is in. Suppose it's set two, and always try to find all the other characters in set two only. So if they fall in that set two only, you are still in the valid word. If you cannot find that character in the set two, it's not a valid word. Right? That's what the problem says. All of your characters should be in the same set or same row.
The input is only have the character only, right? No number and no.
No, so it's written. You may assume the input will only contain that.
Okay.
Even if it's a number or something else, it will just increase the space from 26 character to a 256 ASCII byte, right? The number of rows in the keyboard will already remain same. There will be 4 or 5 maximum rows.
Yeah. So if that's the case, we only need 2 sets. We don't need 3 sets.
Sorry, why do you need 2 sets?
I mean, 3 rows, right? So, if you only need 2 sets, that means, either in set 1 or set 2, otherwise it have to be in set 3. I mean, you implicit,
Right. So
you don't
in
need it
that
explicitly.
Okay. So in that case, if the element is in third set, you will have to always compare, values in both the sets. You'll have to compare, suppose you get a first character as Z. It's not in set 1, not in set 2. Now for any other character that comes in the word, you'll have to always check whether that falls into both of the sets. Both of the sets are there. If it does not, then that's correct. So it's just, adding one more comparator, even though it will not matter from the time complexity point of view. It will essentially reduce some space, but we're essentially talking about very constant space. So it will not matter that much.
Yeah. So the other way I can think a different data structure is using a constant array. So this only 26 character, right? So each character we map to, let's see, row 0 or row 1 or row 2, right? So we keep track of what row we currently in.
Right. That's exactly the approach I think we started with. The only difference was we started with the hash map, but yes, hash maps and all, they have some internal overheads which arrays can optimize. So probably yes, we can go ahead with arrays, to define our positions like Q, A, and all. They can be represented as indexes in a simple 26, position.
One doubt that I had, like regarding the approach using arrays or hash sets versus hash map, was like, if I want to check, let's say, a character in the given string, if it exists in the set or not. So the time complexity of checking if a element contains would be a logarithmic type, right? For a set.
So sets and hash maps from the key point of view work very similarly, right?
Yeah.
Asymptotically, you can consider they have a constant time, right?
Okay.
Because of the hashing mechanism that is used. If it's a really unique hashing mechanism, it's constant time. But if you have any clashes, hash collisions, then only it increases. So from a normalized point of view, from a asymptotic point of view, we can look all the lookups in a hash map as constant time.
Okay, so it won't affect like whether I use a hash map or a hash set.
Right. So hash map and hash set, from the key perspective, they both work similarly.
Okay.
What about the difference between set and a list?
Sorry, could you repeat again?
The difference between if I use a list instead of a set, array list.
How will you look up in an array list?
List
And
dot
what will be the time?
contains.
Right. And what is the time complexity for that?
I think the elements that are present, I'm not sure about. I think it
Right.
should
So,
be the number of elements.
right. So that is in linear time, right? And from hash, what we get profit is having a constant time.
Oh, okay. I thought even for set, you have to go through the entire set or no?
No, so the hashes, hash maps, and hash sets work in a way. So they take all the keys, convert it into some sort of a hash, and
Mhm.
internally, what they do is some sort of bucketing, where they can put the values there, and kind of map it to very internal, specific location-based things. Like they know that this key will be in some specific bucket, and then they try to search in that only bucket, right? That
Okay.
bucketing, there are multiple ways of implementing hashing. I would suggest go to some site and just look at how the hashing works. There are different approaches. So kind of, if you, that's what I'm saying, in worst case scenario you will have collisions in a hash map where the same key internally will refer to multiple locations, but from the user point of view you can look at hash maps as a constant time. That's the main use of, that's the main difference between a hash map and an array. The arrays, if you want to find anything, you'll have to either use indexes or search through the entire array.
Mhm.
Whereas in case of hash maps, sets, you get that constant time lookup using the keys.
Okay, sounds good. Thank you.
Anything else?
I think we can move on to the second question.
Okay. Yeah. So the second problem today from the medium bucket is domino and promino tiling. So essentially, what it is saying, you have two set of tiles. Okay, one has only 2 bricks, and another has 3 bricks, but in the form of a L. So this is called a domino, and this is called a tromino, right? Which is essentially a 3 brick layout, and this is a 2 brick layout. Right now, the problem is you are given a 2x n board, and n can be anything. Right now, you have to tell in how many ways you can arrange these x's, these dominos and prominos, such that the board is always filled. Is the problem clear, or should I explain it in a different way? Let me share my whiteboard. So essentially, the problem
By
is,
2n board.
yeah, I'm just going to explain the problem here. So you have two kind of bricks. One is, this is a domino, and then you have another which is a tromino, right? Now this is essentially a 1x2, or if you look at reverse way, it's 2x1, and this is another way of looking at a tromino. So right now you're given a board which has only 2 rows, right? And suppose the size of the board is 1, 2, 3, 4, 5, 6, 7, 9. Let's say it has 9. So it has 1 column, 2 column, 3, 4, 5, 6, 7, 8, and 9. So this is a 2x9 board. Now what we are told is we are asked to completely fill this 9 box, right? We have to completely fill this one, right? 9 box one. But now they're asking in how many ways using these two kind of tiles can you fill it? Okay. So let's assume we have only, for the sake of understanding, let's assume we have only 3 by or 2 by 2 box, right? So how many ways can we fill it with either domino, tromino, or the combination of them?
We can fill it in 2 ways. Like one only with dominoes we can fill because we have to fill it completely, so we can't use trominos. So we'll each place 2 vertical dominoes or 2 horizontal dominoes to completely fill this
Right.
arrangement.
So you have 2 options. One is this way, another is this way, right? Correct?
So how do we know this cow? The cow is 2. I mean, like, is that a cow is based on the It's not based on the number of tile or based on the number of the tile layout.
I'm sorry, I did not get your question.
I think what he's asking is, I'll explain if I try to. We are given a two by n board. So n is the number of dominoes, and we only have like 2 rows. We have to fill the board completely, only using these two given type of dominoes. So that's the constraint here. The board is only 2 rows and n number of domino columns.
Okay.
So I hope that was answered.
Yeah.
So the answer of this 2 by 2 is like we can arrange it in 2 ways.
Right. So this is one of the way, and this is another way.
So
Right.
like 2, yeah.
So now let's look at a bigger section. For the sake of clarity,
Let's start
let's
with
look at
2
a
by
bigger
3.
Yeah, let's start with a 2 by 3 one. It's fine. So how many ways do you think you can fill it up with dominoes, dominoes, or any combination of them?
One is if we can place the L-shaped. One
So
is
you're
in
saying-
straight.
So we'll use the first one as L shape. What next?
And then rotated L.
Okay, then rotate it as right.
Yeah.
So this is one of the questions, right? And what
Yeah.
else?
One is like dominoes, only two domino, arranging 2 horizontal and 1 vertical.
So 2 horizontal and then
And
vertical,
1
right?
vertical.
Right. And what else?
I don't think so.
Would the order matter? Like, if I have like 1 vertical and 2 horizontal, is that the same or that's different?
Oh, that's a different layout, right? So we're talking about different ways to arrange it. If you have sorry, go ahead.
Go ahead, go ahead.
So I was explaining, if you have first 2 horizontal and then third as vertical, it's a different layout or different arrangement as compared to if you have a first one as vertical and then other 2 as horizontal.
Then we can do exactly that, like 1 vertical, 2 horizontal. And then
In the first,
In the reverse way, like 1 vertical first and then 2 horizontal, like that.
yeah,
Sorry, okay, yeah, go ahead.
like all 1 vertical and 2 horizontal. Then all
1
3
vertical
verticals.
and that's correct.
We can also reverse the first one, so we have another layout.
Exactly.
Yeah.
Right. So anything else you can think of?
I think that's it, I guess.
Okay. So now somebody, as the problem is clear, so somebody would try to, take a hands on what is the approach or any idea about how this can be done.
One approach that I was thinking is that like this is the smallest problem that we can break it down. So let's say we are given any number. Let's say if we want to solve it for 4, right? So we already know that like for 3, 2 cross 3, we can solve it in 5 ways, right? So we can we just need to find out like what happens when we add another space, right, for 4th. So if we know we can solve it in 5 ways, right, and then what will be left for, we already know for 3 spaces we have solved, right? For the 4th space, what we can do is like how many ways can we solve the for one option, right? So maybe we could like multiply it by like these 5 combinations into 2, because we can shift them by 1, right? And just add a vertical domino tile there. So the answer for that would be, I guess, 10.
So
Yeah,
let's think about, we have 2 by 2 right now, right? So before
yeah,
that, we would solve 2 by 2, and we see there's 2 ways to solve it. And now
yeah.
it's 3 by 2. Then how you extend from that?
Yeah, so for 3 by 2, like we have another solution for those domino tiles that come into play. Only when the number is greater than 3 do these domino tile combinations come into play. Otherwise, like if we have only 2 more spaces left, we can only use the vertical or the horizontal combinations, both vertical or both horizontal. Like if we have less than 2 or 2 tiles, we only have like 2 permutations available. If we group it into like combinations of 3, maybe then we can solve it further. Like that's what I was thinking.
Yeah, I see that when we have 2 by 2, we have the first and the fourth diagram on the right, right? And I don't see how we can extend from that to build 2 by 3. Because we have only, well, 2 by 2, we have only 2 configuration.
So guys, can we look at it in a different perspective? Like if we have something built up, like suppose this is already a filled array, right? Suppose we have a filled array, right? And what is that, you can either from the end, can you either remove a domino or a domino, right? And then try to see if there's a sub problem which can be recursively used, right? So let's assume we remove a domino from here. We are reducing the problem for finding the number of ways from n to n minus 1, right? So if there are supposed 10 ways to get this n minus 1 filled, all of the 10 will be applicable for n, because for each of the combination you're just adding one domino at that, right? Is it
Yes.
right? Let's suppose you're removing a domino from there, right? Suppose you remove this one, and this one is removed. Then what does it give you, right? You're at the end, you're right now just left with the n minus 1 state, but which is having one as a one partially filled, right? Partially filled section, which is this one, right? If you consider n minus 1 here, you have one partially filled section, one filled section, right? We'll see how we can get this state if we want to calculate how many ways are there to create this state. But right now, if I can say there is a way, if I can remove last domino from that array, what I need is number of ways this structure like this can be created, right? And this will not be once, this will be 2 times. One for this sort of domino, other is exactly opposite, right? Which will create a structure like this. Is it clear till now?
Yeah. But so how do you count? You count the number of plus previous, the number of ways to create the previous configuration plus 1?
No, so if you say there are 10 configurations for previous state, so what you're suppose there, so let's assume there are 10 sequences, right, which
Okay.
give rise to this one. And if you're appending every sequence, at the end of every sequence, you're adding T, which is Tromino, it's still the same number. So if you get the number for n minus 1, it's essentially same for n also, based on this condition, right? Everything we are appending just T at the end. Right. So essentially what we are saying right now is, let's assume f of n is number of ways I can fill, number of ways I can fill till n columns fully, right? The full completion. And E of n is the ways I can partially fill the last section till n columns. So now based on these three, what we are saying is, if you want to calculate number of completely filled positions till nth column, what we need is to find number of total filled ways for n minus 1, which is essentially this state, because at the end we are just adding one domino at that, right? And what we decided were there were two states that we can create and use the Tromino at the end. So 2 into number of ways I can create this partial array, this partial state of the 2 cross n, right? Partial state for n minus 1 rows, n minus 1 columns, right? Is this clear till now?
Yeah, I think we can move on.
Guys, everyone clear about this?
Not,
Can you repeat
yeah,
again?
not completely clear to me.
Sure, sure. I know this is a bit different to understand in the first place.
Yeah, the example which is the input 3, if we try to use that next one.
Yeah, let me just use that example. So let me do this thing. Suppose we have this 2 by 3 matrix, right? Which is essentially, suppose it's completely filled, right? Now there are the number of ways I can get the count of this is if I remove this one domino from here, right? So what is essentially left is a 2 cross 2 matrix, right? And how I want to find the number of ways in which it is calculated, let's park it for now. The other way is I can reduce it by this much. Sorry, I can do this one, right? And this part is another terminal which I am removing, right? Is that correct? Is that understood till now? Right.
Yeah.
So now in this we are left with a 2 cross 1 partially filled array or partially filled section till n minus 1 row. In this case, 2 rows, right? 2 columns, sorry, 2 columns, right?
Mm-hmm.
Now we know for the base case 2, we know this is always going to be
Filled.
2. So
Yeah.
there are 2 ways to create a 2 cross 2, right?
Yeah.
And there are for 2 cross, 2 cross this, there are always going to be only 2 ways to create this kind of metric also. So if you can create it this way, or you can create it this way. Is that correct?
Yes.
Okay. So now when we are here, we know how many ways, if we just use this one, now we are just, coming back from the, recursive condition. We know there were 2 ways to create this 2 cross 2, right? And we can use all those combinations to create a 2 cross 3 also. So we have 2 ways to create this sort of structure. So some combinations of 2 cross 2, and at the end, everything is attached with this. Yeah, is it clear till now?
Yes.
Okay. So now coming to this condition, the other one, right? Now, how can you create a complete array for this one? You can attach a Tromino to this, right? So the way we denote it, so we know the for 2 position, there will be 2 ways to create this, right? Or rather, there are 2 ways to create this, right?
Oh, are you talking about like you're just removing the Tromino in the way that you've mentioned in the first one, or are you considering those 2 possibilities as the rotated one? Yeah, once you
The
have
one on
rotated.
the arrow.
The 2 rotated possibilities.
Okay, okay.
Right?
Yeah.
So now consider these 2, and then you can extend these also by the Tromino that you have removed. So what essentially you're doing is trying to find how many ways this can be created and just adding this Tromino at the end, which will give you again like 2. Right?
Yeah.
So the
Okay,
first
so this,
I have a question. So the first Tromino and from the previous case is attached in 2 ways, and the new one can be attached in 1 way, right?
so sorry, for which case are you taking? This one, this case,
So
bottom case or
for
the top case?
bottom case, for the Tromino,
Mm-hmm.
for
Mm-hmm.
n-1 case,
Mm-hmm.
like the existing case, like the previous case, you can attach it in 2 ways, which is on the
Right,
arrow, the upper and the lower one. And the new
correct.
one can be attached in 1 way.
Right. So for each of them, there will be 1 possibility, right?
Right, right.
Either for
Okay,
this, either for that.
right. Okay, got it.
Right? Which will give you again 2, and you can sum it up. So this will give you f of n, which was essentially the, let me just, if I can go. So what we just did in the diagrammatic way was the equation that was generated on the, yeah, this equation that we did. Plus twice times of p of n minus 1. Correct? So this is, if we remove the domino, where we remove the last part here, whatever was there, and calculated this part recursively. And this one was where we took the 2 cases, like this one, and sorry, this one, and the other was this one. Right? Now the question arises, how can we find partial cases? Right? How can we find, if I know I need a partial state to calculate the final state, but I need at each step, I do need a way to calculate the partial state also. Right?
Hey Puneet, quick question.
Yeah.
So when we were deriving the value of 2 cross 3, uh, did we reach to total 4 combinations just now? Because there were
Actually
like,
reached it.
2 cases in the top when we were using tile, domino, and then,
No, we got 5 cases.
no, when we just used this, couple of minutes back, there were 2 pictures. One was on top and one was on bottom, right?
Let me check if I can get back there.
Yeah. Is it a control Y works?
or is going only till here.
Yeah. If it works, then we can go there.
It's not working. So, sorry, Roger, I did not get what you're trying to say. Should I clear
So-
the screen and try to it again?
Yeah, quickly let's do that. You already know so we are deriving solution for 2 cross 3. We are starting with already for 2 cross 2, we know there are 2 ways, right?
Right.
And then you added a tile on right side. So there were 2
Mhm.
solutions, right?
Right.
And then you had you were using Trominos.
Mm-hmm.
So that gave you 2 ways again, right?
Right.
So what my question was, are we saying
Oh,
that for
I missed one case actually.
exactly? So that's why I
Yeah.
talked about it.
Oh, sorry. Thank you for
Yeah,
getting
no
that.
problem.
Yeah, I actually missed one case. So we know this is so let's say this is the condition where we are removing this Tromino, and from here we are removing this Tromino, right? Now we know for this one, we are going to have one way to create this structure, right? From a 2 width, 2 cross 2 section, we can only have one way, right? So essentially for each of these, there will be one structure created, and this will give us 2, right? For till here we had derived this one, right?
Yeah.
Yeah.
Right. So there was one structure, I don't know if you remember, there was this structure that we had discussed. Not this
Yes.
one. Uh, I actually forgot let me do it with show it with the 4 one. It's pretty easier to, right? So let's say we are removing this one, okay? And then we are trying to create a structure like this. When we go one step back. So Roger, this is the case, right? Which you are discussing.
Right. So if you, yeah, exactly same way, if you consider that your last block was 2 horizontal lines, 2 horizontal dominoes, then your problem will reduce to n minus 2. Like if you are calling Fn as the main problem, then you have reduced it to Fn minus 2, because that's what we are missing here.
Right. Because because the thing is, if you take n minus 1, there's no way you can get this structure in n minus 1 condition.
Yeah.
Right? So that's why we have to consider this slot also for calculation.
Yep.
Is that understood? So this structure which we're discussing, the last one, if we are taking only one domino from the last, we are considering a shape which will remove this part, which is essentially a single domino vertically, and then you can get what is created essentially from 2.2, which is complete. Now, if you take a Tromino like this L structure, you're still cutting one of those structures into half, right? Now, this structure where you have last 2 completely filled with horizontal, this you cannot get in any of the way that we have described till now, right? This structure, or this structure. That's why you have to take this structure and reduce your problem from n to n minus 2 also. Does this make sense? Or no?
Why n
Let me,
minus 2?
let me create these mappings. We have this 3. We have this another way of creating 2 by 3. we have this one way, another way of creating 2 by 3. Right. I'll just map each of the possible solution with the formula that will be created. And here is the fifth one, right? So this one, if you see, if I can cut this into vertical half, I can get a solution for these two using the first part of our equation that we discussed. I'll just remove the vertical domino and try to find how many ways I can use a 2 by 2 fully, right? This is our first part of equation. Now from the second part of equation, what I did, I removed a domino from the end. So in this, I can remove this domino and this domino, which will essentially take, what I'm doing is partially filling this till 2 of 2, right? This was second. And now if you see this one, this third condition, if I try to only take n minus 1 elements, what I'm doing is I'm missing a complete configuration, which is horizontal 2 elements. Both of them need to be horizontal, right? So that's why what we're doing is we are considering a phase. Instead of removing a vertical domino, we are removing 2 horizontal dominoes and then taking all the combinations that can be created before that, which is n minus 2, because the width of this domino will be 2. Is this better?
Yeah. Yeah.
So in last one, so you are saying you will be removing the 2 width, the domino with 2 width. So that's why it's n minus 2.
Right, that's correct.
Earlier we were removing 1 width one, so that's why it was n minus 1. Here we are removing 2 width domino, so that's why it's n minus 2.
That's correct. Because what we are looking is whatever is before that, it's completely filled.
Okay.
Right? Same way here. Everything what we are looking before is completely filled. Completely filled. Only in this case, it's partially filled with one section or one part of the tile empty. Is this okay?
Yeah.
Now the only challenge remaining is how do we find this partial? How do we calculate the partial fills? Okay. Is that okay? Why do we need to find the partial fills? Do we understand that thing?
Yeah, we need to find the partials of all these dominoes to calculate our answer. Like, is this
Right.
like, yeah.
So suppose we have a filled 2 cross n bounded area. How can I create a partial for this? Like I want a section which is partially filled to n. So this is my n. Okay, and this is something, before. I want to create this structure from any of the existing structures. Let's assume there's nothing wrong. I want to create this. How can I do that?
Some way if we can check that the upper rows and the lower rows which are completely filled or not. Like here we have filled upper rows, but not lower rows.
So can we think in terms of, if we have this structure at the end? Because anyway, we have to look in terms of dominoes and dominoes, right?
Yeah.
So what if this is nth row? Can you see any relation to what we are discussing for calculating fulls, similar to that a relation for calculating partials? So if you see, for calculating partials till n, what you can do is whatever you have full till n minus 2, right? This will be n minus 1, this will be n minus 2, right? So all of these n minus 2, if you attach a domino to them, right, they will create a partial. Is that correct?
Okay.
And the other way to create a partial is if you already have a partial. So suppose you already have this as a partial. Now can you remove a domino from it or add a domino to it? So if you want to create this kind of structure, only way you can do is attach this domino here, right? So if this is n and you want to find the partial till n, what you can do is simply take partial of n minus 1. So if you have calculated the number of ways you can get partials till this point, you can attach a domino to the other side, which is empty. You will get another partial, which is still n. Does it make sense now?
I'm a bit confused over here. So why we are going for n minus 1? Earlier we were going for n minus 2.
So that was when we were calculating the fully filled sections, right? Now what I'm doing is I'm trying to find partially filled sections.
So let me give one liner what he's trying to do, then it will make really more sense. What we are trying to deduce is a recurrence relation. So, you are trying to find solution for the smaller values of n. And what Puneet deduced that there are two players here. One is like a full solution is could be solved with a couple of full solutions plus partial solution. So now he has a recurrence relation between two full solutions for sure, but it depends on a partial solution. Now he wants to somehow reduce that, like, formula for that partial part to further smaller values so that he can actually use dynamic programming or anything to go to the base case, and then he can, do a bottom up to figure out the solution. That is why now he's trying to look at, okay, what are the possible configuration for the partial ones, and what are the possible ways to create that partial ones from a smaller values. And then he is trying to deduce this formula. I mean, that is the context. Like, if you know the context, then you will know why we are doing that. And then, there are only a couple of ways to do that. Right, Puneet?
Yes, that's correct. So essentially what I'm doing is you have a base case and how you can use already created cases to find out what will be your final result. So essentially that's why we are doing, taking a last section, removing that, because if we are trying to find this and we somehow know the solution of this, we can just reuse that solution and get the solution for the next state also. So here, each of your state and the movement from one state to another is either adding a domino or removing a domino, or adding a domino and removing a domino. Right? So what I would suggest is go through the, I'll share one video. It's a Geek for Geek video and they have explained it really well. Probably I'm not that good at explanation of this problem, but they have explained it really well, how, the concept of dominoes visually also, and go through the solutions. It's a pretty straightforward solution, but just this thought process of building this entire, structure or configurations and looking at how they are related to each other, that's the time consuming process. Otherwise, the program in itself is very simple.
Can we assume it something like, let's say, at first stage, let's say, instead of going backwards, let's say if I'm trying to visualize it, is it something like I'm first placing on each level, I'm placing either a vertical block or a horizontal block, right? And then whatever the valid paths I can continue on, like if I place a horizontal domino, then I have to in the next step place an horizontal domino only, because I need to completely fill all
Right. So,
all the board.
Right. So what you're doing essentially is kind of backtracking.
Okay.
Right? Because you are trying everything and then looking if that make configuration, otherwise you'll remove it and then add it back.
Yeah,
What we are doing here is, we know that the final state is complete,
okay.
and we are just using the states which can move. So it's like, you know the final state, you know the source state. And instead of moving from source to destination, right? And you know the transitions in between. It's a domino or a domino, right? What you're doing
Yeah.
is essentially moving backwards. So instead of adding a domino or domino, you are removing a domino or domino
Okay.
and trying to reach to some state which is again source.
So if I'm going to like summarize kind of a thing, like you're moving from all the valid paths instead of like, for in this approach we would be like ignoring or pruning the paths which don't yield to a full result. Instead, what you're doing is removing
Exactly.
one. Yeah,
We'll never
got it.
go to a situation where we have this kind of structure, right?
Yeah,
Because
got
we
it.
know it will somehow convert to this by adding either 2 domino or 3 domino.
Mhm.
So we are just avoiding to go through those paths.
Okay.
Okay. I think we are running a short of time today, so let me move to the next problem. So the final problem for today is sliding window maximum, right? This is from Hard Bucket, and the problem statement is something like you have a number of elements given in an array and a value k, and what you have to do is you have to implement a sliding window for the size k, and for each of the window you have to output the maximum element in that window. Like suppose in this case the first window is 1 3 minus 1, so the output is 3. Now second window has 3 1 minus 3, output is 3. And then we move sliding window by 1, and then just check out what is the maximum here and then output that. So this array 3 3 5 5 6 7 will be our output array. So any approaches, ideas?
Are we to like find the sliding window maximum in this problem? We need to find the maximum sum in each of the rows of this
No,
matrix.
we have to output the array of these maxes. So for
Okay.
each sliding window, so this is the first window, you have output of 3. For next window, you have output of 3. For next window, you have output 3. And your output, the result output of the entire function will be an array of 3, 3, 5, 5, 6, 7. The max of each slided window. Okay. Go ahead, guys. Any approach, anything?
One approach is like how it is a sliding, like we can add one by one in that bucket, and then after moving forward we'll be removing the first one and adding another one, like how sliding moves, like taking a 3 3 sliding windows.
Right. So in this case, when you move from 1 3 minus 1 to 3 1 minus 1, you will remove minus 1 from the bucket, right?
I'll remove first one, which is 1 from the bucket, and add minus 3 to it.
Okay. So how is it helping you to find the max? That's
So
the thing,
there would be another function which will be calculating the max, just giving this array.
correct. So you will be doing a sweep of the array one by one, and for each of the window, you will calculate the max using some linear function, right?
Yeah.
So what will be the time complexity for that?
This would be like more than an n, which is maybe an n square. Like n log, it would be n into k, I think.
And what if our k is n by 2? Well, it will go to the worst case will be when you have k equal to n by 2.
Yeah.
Right? You will have a complexity of almost n squared by 4. N squared by 4, yes.
Yeah. Like n square only. Yeah.
Okay. can we make a like max heap of the sliding window and then just keep on adding elements and then like checking to create the array? We'll just get in constant time what my current maximum is in the heap, right? And
Okay.
then just remove the element and add the next element of the window, and then do this approach for all the elements. Like that would be, I think, a better approach.
How would you remove the element from the max heap?
Okay. Like I don't like I'm not sure about the complexity of it. Okay. But I think the heapify function is a log n times, like I'll just create a max heap of k size, and first I'll add those k element, then I'll remove my first element, and then I'll add the next element, so I'll automatically get the next position of that.
Right. So if you heapify that small element again and again,
Okay.
heapification is an n log n procedure. So for the k side, it will be n k log k, right?
Yeah.
And that activity you will do almost n minus k times.
Yeah.
So that for the worst case of k equal to n by 2 will become n square log n.
Okay.
So there is one
Right?
another approach of this, which is a segment tree approach.
I am not sure. Could you just explain? Because I'm not aware of how
So
I can implement this.
how segment tree works is like, if we know the start and end position of that particular the range which we need to find, then we can easily go to that particular start and end position and find the max one. So how segment tree works is like, where our children's are all these the numbers which array which we are having, and how they'll be becoming. Like, first of all, we need to find the mid, and the left side of the mid is the whole which is in the range of 0 to mid, and the right side of is like mid plus 1 to the end. And
Would it be
similarly,
possible if you
we'll be
can,
subsetting all these.
Sonia, would it be possible for you to share the screen and probably draw this?
Yeah, definitely. I'll do
It's
it.
a bit difficult for me to understand this.
Oh my God. Actually, I think you need to
Yeah, I'm stopping.
stop sharing.
I stopped to share.
So how this will work is like, for example, we have an array of this 1, 3, -1, -3, and like 5, 7, something like that. I'm not good in this. So how this work, and each children, for example, here we have 1 and 3. If we take the maximum of these, we will be having 3 over here. So how this will be going, we'll be having mid. Our mid is over here is 2, 3, 4, 5. Mid is over here. So we'll be going, this will be the left and this will be the right. So here, so now we'll be having again -1, and we'll be taking 3 -1, and this, our max over here will be 3. Similarly, we know that this would be the right point. So we'll start with like 3, 5, and take the maximum of it, which will be 5. and while taking the 3, 5, 5 and 7, we'll be having 7 as a max, and then all of these would be having the max is 7. So here we know that the range of this that this 3 is in the range of 0 to 1. Like when we are creating any node or any data structure, we'll be putting the values of left child and start and end main point. So this particular node is having the start and from 0 to 1. And similarly from this particular node is having from 0 to 2. Similarly, so you can see that these all are here, all the children nodes are the points of the array which we have created. So this would be like the n, if we have any n number of n number of arrays, n number of elements in an array, then our nodes will be like 2n minus 1, because yeah, so it will be a full binary tree, because either it will be having a 0 or 2 children.
Got it. And how much time would it take to, space and time complexity would it take to create this tree?
So it's a log k, like I would say log n, because we are going for finding a middle part and then moving left or right. So in a worst case, if we need to find the part which is from 0 to like something over here, let it be 6. So this is let it be 6. So if we need to find something from 0 to 6, then we half of we need to cover from here and half we need to check from here, like something.
Makes
So
sense.
which will be like how we are creating like till our mid part from here, like from starting to mid of here, and then mid plus 1 to this particular.
So essentially what you're doing is creating this new data structure which will take up, suppose, n log, big O of n space for this entire structure, and then using the indexes to find the max within that range.
Sorry?
Is that correct?
Yeah, finding the max in that.
Okay, so that will again be, if I see from the space complexity, it is big O of n for creating this entire segment tree again. And
So while we are creating a segment tree, we'll be going, we'll be creating that, I think, in a log n times, because for each operation, either we are going for a left or we are going for a right.
yeah, that is after you have created this tree. So you don't need to create this tree, do you? There will be a data structure for this, right? I'm assuming that there's a separate data structure for segment trees.
Yeah, it's a data structure. Yeah, different data structure. First of all, we need to construct this tree, and
right, so that's what I'm saying. When you construct this tree, you need O of n space to store this, right? Or am I missing something?
So it's maybe because it's more than, it's not a space. Yeah, because it's more than I would say n, because we have to put those n minus 2 n minus 1 values as well, because these are the children which we are storing, but after that we are storing these sums as well, like max as well of these.
Right, so that will be, if you have all the elements of leave n, and then minus n will still be 2 of n, 2n. In
2
the
n
order
minus
of n.
1. Yeah.
It will still be in order of n.
Yeah.
Okay.
So actually similar thing you can achieve using binary search trees provided by, like in Java, we have tree set, tree map. Even in C++, there must be something similar. And you only have to have k size of your tree set or tree map. And then everything is O of log k there, right? So as soon as your size increases more than k, you can remove an element in O of log k.
Okay.
And the problem was with the heap, that was like O of it was not O of log k. That was the problem with the heap approach somebody suggested. So this is
Okay.
definitely much better than that. But I think since we are running out of time, I think Puneet is going with a better solution, right, Puneet?
Oh, I think I'll go with the approach that is suggested there for the linear one, because we have already discussed all of them except for one. I'll just add to the heap one. So instead of always removing an element from the heap, your concern should only be with the max, which is at the top of the heap and it's out of the bound. So if it's out of the bound and it is at the top, you can just remove it. You don't need to consider anything which is inside the heap but not the max. Right? So if you're going ahead with the heap approach, you put some values in,
Yep.
right? And suppose you're at index 4 and the max
Okay.
that you're seeing right now is at index 0. You don't need to consider it. You can just remove it from the heap and then look at the next value.
Okay.
Right? So in the worst case, it again has that space complexity of O of n. Okay. But yeah, the approach from that point will work. It's just that the space will be O of n.
Okay.
Right? And the time complexity will be n log. Actually, n log k. In the worst case, it will be n log n.
Yeah.
Okay. So I'll just, Sonia, if you could just stop the
Yeah,
share.
sure.
I'll just go ahead with the approach that's mentioned here for the follow-up question. So the follow-up question here says if you can complete this in O of n time. Right? So if you see the array, we just copy the data points from array. It's 1, 3, minus 1, minus 3, 5, 3, 6, and 7, right? Now let's consider the first window. So I'll just, have some pointers and let's see if those make sense. At any point in time, if there's a window which has 3 in it and there's a 1 before it, will it ever happen that 1 can be the maximum? Just take any combinations, any combination of, size of k, that these two elements are there and any one of them can be maximum. Will it happen ever? So let's take this size, that's 2, right? Both of them elements are there. It will have 3 as maximum. Let's take 3. It will still have 3 as maximum. Let's check this. It will still have 3 as maximum. Okay. Anyway, if you are having this 1 in place, or it is one of the candidate maximums, it will never happen that this is a final maximum if you have a higher element after it, immediately after it, or even after it for some reason, some spaces ahead. The reason being, if you have this element added in a bucket and this one is also added, at some point in time, you will have that element, the one before it, removed from the bucket, but this will still be there, right? So it will never happen that these two elements are in the same bucket. The one which is smaller on the left will ever be a maximum. Does this make sense?
Yeah.
Right. So essentially, what we are doing here is kind of creating a reducing monotonic stack. Right. So we'll have 3 here, and then can -1 be a probable candidate in future? Yes, it is 1, and sometime when 3 is removed, it may become a probable candidate of maximum. Right. Now -3, it is still smaller than this, and yes, it can still be a probable candidate, right? Now when I get a 5, right? So this can be maximum, right? But now look at the condition, like we only need 3 elements in our bucket. So the element which is a start, which we'll have to remove, right? Because this will never be now a maximum, right? 3 was the maximum earlier. Now we have an element which is 5. 3 is removed from the slot, so we can remove it, right? And based on the conditions that we were discussing earlier, right? You have 1, 3. Anything which is larger and after the smaller one, it will never be. And the monotonic queue that we were discussing, the smallest queue, that is getting violated here, right? You have -3, -1, -3, and then there's a higher number. Based on the discussion that we just had, these 2 points, will it ever happen that you have any two of these three numbers with 5 in them and anything apart from 5 that is maximum? No, because if you take any combination, if you keep sliding this window of 3 ahead and ahead, till you actually find a value that is maximum more than 5, you'll never change the maximum, right? So in this auxiliary data structure, what you can do is remove everything which is greater than 5 or less than 5, right? So this one will be this one removed. And then you will have only 5 saved in the auxiliary data structure. And this one will be your candidate max value till the time either 5 is removed, that means it moves out of it, or there's an element which is greater than this comes into the picture. Does it make sense?
Okay.
Can you just explain it with an example or this only with the auxiliary data with a working example?
So let's say this is the auxiliary data structure, right? So I start with 1, suppose, and I'll put 1. There's no element, so this is 1. Now there's an element called 3, right? So now based on the condition that we discussed, right? If 3 comes in and there's a smaller element less than that, it will never be a probable maximum candidate, right? So we'll remove this. Okay, I'll just remove it and put 3 in that place, right? Because that's the new maximum, that's the new probable maximum candidate. Now there's a -1 that comes in, right? Right now I'm still in the same window, right? So -1 comes in. In future, when these elements move out, yes, this can become a probable candidate. I'm not sure till now, but it can become. So that's why I'll just keep it here. Does it make sense till now?
Yes.
Okay. So now what I'll do is I'll move my window and go to the next section. This is my new window. So when I move the window, I know I have to remove 1. But 1 is nowhere in the auxiliary data structure, so I don't need to worry about it. Right? The reason being I am already removed 1 because 3 was there. My max will always be at the first position. Right? And then the future maximums will be somewhere down the line in the queue. Right? Now I have next element which is -3. Again, based on the same logic, -3, yes, we can put it in because in future it might become a potential maximum element. I move my window again. Now I go to -1 to 5. I'm removing 3, right? Because I'm out of the window. And I look at the top, yes, this is the element which is getting removed. So I'll remove this one, right? I'll remove this element from the auxiliary data structure. And the new element getting added is 5. Now, if you see 5, it's a new element of the auxiliary data structure, right? And it is greater than any of the elements that are already in, right? And anytime we get a data structure which is greater and there are smaller elements after it, they will never become the maximum now again. So what I'll do is I'll remove this one, I'll remove this one, and I'll put 5 in there. So now this is the head of my queue structure, right? Or the auxiliary data structure. And this will point to the maximum. Now, similar way, moving ahead, now my next element to be added is 3. And my element to be removed is -1. It's not there, so I'll move ahead, keep moving ahead. Till the time I'll add 3 and then 6. Now when I'm adding 6, I'll have to remove all 3, 5, and then add 6 here. Because all of them are smaller than this one. And the final step will be when I add 7, I'll be to remove 6 and then have 7, right? And every time you see I'm adding and removing, I'm moving this header pointer. Now header or the pointer which is pointing to my max element, right? And anything which was added or removed before is now not of no use. Does it make sense till now?
Yes.
So now only data, the thing that we need to look into this is to get it a completely N algorithm is how can we have this data structure optimized so that the removals and the additions that we are doing, they are done in constant time. Constant or minimum time. Right? Because we see, all the elements that are being done here, right? We access them once, right? And now the only thing is how we can reduce these elements.
And also,
So this is where.
sorry, go ahead.
Sorry, Raja, go ahead. I was just giving the solution.
Yeah, also observation, because you do it pretty well, that we are doing this activity from both the ends. Because three, for example, its lifespan, finished, and it has to draw from left side, and a new candidate will come from right side, and there could be more candidates which have lesser values. They have to go from that side. So there are two ways to die, right? One, your lifespan finishes. The other one, someone better than you have come. So now that will give you more context which data structure to use, because you can think that way to deduce that.
Yeah, so this is somehow kind of a data structure which can give you properties of both stack as well as a queue. And any guesses on the data structure? Don't worry, guys. This is the first time I even heard about this data structure. So there's something called as DQ. It's essentially nothing but a doubly linked list that I can understand from the raw. So you have each element, and you have pointing it to both the ends. So this will be your start, and this will be your end. So all the removals that you're doing is from the end. And all the removes from the start, you can use it during the start point. And additions, you can use the end pointer. So there are a couple of STLs also, I think, in Java, and I was in other DQ something, DEQUE, which can give you an array-like interface, but internally it has this doubly linked list implemented. Guys, is this understood? Confusing?
Yeah, any questions on either the approach or the data structure? Please come now. Any questions?
But isn't isn't it showing the behavior of a queue only, because we are removing from one end and then storing from the other end? Why it's a DQ?
We are
You
removing from both the ends, right?
Yeah.
We are removing, as Roger said, we are removing from the front of the queue when the lifespan ends, but we are also removing from the rear of the queue when there's a better element found.
When there's a better element found. Okay, okay.
And also we touch all the elements exactly once, right? Most likely just once you look at it. So definitely it's this is the best you can.
Yes, even in the auxiliary array, you will use that element either during the time of adding or during the time of deletion. So at max, each element will be added, touched only twice, max. Once when you're iterating the input array, and once when you're, adding or removing it from the auxiliary array, which is essentially the DQ. Okay, if there are no questions, then can end the session.
One thing. Okay, fine.
Yeah, go ahead.
Okay, so let's say the window size was like k. The k is equal to n. So how would we proceed? I first everything can be a candidate key kind of a thing, right? If let's say it's a like sorted array kind of a thing, right?
Everything
So
cannot be a candidate key in that also, right? Because
okay,
when you are creating this auxiliary array, so suppose you
mm,
put in 1 and then you are
yeah,
putting in 3, right? So it is removing the candidature of 3,
okay,
right? And then you put -1, -3, 5, and then 5 will remove candidature of every other element which is smaller than before that,
okay,
right? And then 3, and then 6, and then 7. So in what will happen, the only case where you may have all the elements in this auxiliary array is if it's essentially a decreasing, array, sorted in a decreasing order.
okay.
Right? It will fill in this auxiliary array entirely. But still, even in that case, the time complexity will be only 1 because it will just touch the element once.
Yeah,
Nothing is
okay.
getting removed from the auxiliary array. It is just one time you are putting it up and pushing it into the auxiliary. And after that, you will not touch the element.
Yeah, got it. Thanks.
I would like to mention one thing also. Like, if there are some other questions related to like find the minimum in all these um, or having the k windows or find the max total of the that k windows, then one that which I mentioned, segment tree, is very useful for all these data for all to solve all these questions.
Okay,
Yeah.
thank you. Okay, we are almost 25 minutes over time, so let me stop the recording, and if someone wants to continue discussion, we can continue. Else we can